Hello, my name is Barbara Herdt from Laser Components, Germany. I'm responsible for laser optics at the company and work for more than 15 years in this field. Today, I will talk about coatings for laser optics on the next generation due to technology and new measuring possibilities. I will first give you a short introduction of laser components and what is our expertise in this field. One topic will be different coating technologies and what is good to know when deciding which to use or what you should consider when specifying optics. Finally, I will provide an overview about measuring and monitoring during the coating process and which new product could be achieved. Let's start with a short introduction of laser components. The laser optic production started at Laser Components more than 35 years ago, just 4 years after foundation from Laser Components. Initially, we started with the E-beam chamber and were soon known in the German market for custom-specific high-power coatings. Constantly, we increased the in-house coating capacity and technologies. Today, we have the 3 leading coating technologies available. Constantly, new measuring equipment is added for better documentation and testing. Our focus is to use our knowledge on thin film coating designs to increase the damage threshold of our optics. Today, probably 80% of our delivered optics are custom-specific coatings and substrates produced at our facility in Germany. We coat from 248 nanometers up to 3 micrometer, and we do small sizes starting at 0.2 inch up to diameter of 15 inch. We do serial production of several thousand, but also small quantities for prototyping or small projects that 3 pieces are handled. At Laser Components, we do many different mirror, dichroic, output coupler, thin film polarizer for the wavelengths mentioned before. Additionally, we produce Gaussian mirrors at 1064 nanometer more than 20 years. When comparing the coating technologies, I will talk about the 3 technologies we are using for our high-power laser optics coatings. The E-beam technology, also known as PVD or physical vapor deposition coating, is used since the beginning of laser optics production. How is it working? By heating the coating material with an electron beam, this is where it got the name from, the coating material evaporates. This is done under vacuum and the molecules from the coating material deposits in the chamber. In our case, we use a chamber with the coating material at the bottom and the substrates in the top in a planetary rotation system to get an homogeneous layer thickness over the area. To reach a good adhesion of the coating material on the substrates, they are heated up to about 200 to 300 degrees Celsius. Why is E-beam still of interest for many applications? The biggest advantage is the very high damage threshold for nanosecond pulses for standard coatings as mirrors or beam splitters. This can be seen also in many results at the damage threshold competition, where different suppliers provide samples for LIDT testing with different technologies. As the coating of E-beam is not very dense, the coating has not a big influence on the flatness. The other big advantage is the pricing. As the coating time is shorter than for other technologies, the price per coating lot is typically lower. But there are also some disadvantages. This is mainly driven by the fact that the coating is not dense, and for some application, as under vacuum or with temperature changes, the coating is drifting. Because of this temperature drift, the spectral measurement during the coating process is not working very well, due to the different environmental conditions during the coating process. Thus, for complex coating specification, other technologies are preferred. Then maybe ion-assisted deposition or IAD is a good choice. IAD is in fact an E-beam technology. So the material is evaporated with an electron beam. But additionally, an ion beam is accelerating the coating molecules to reach a higher kinetic energy hitting the substrates. No heating of substrates is needed, and therefore we do coatings on optical fibers with IAD. With this technology, a much denser coating than with E-beam can be reached. This is one of the big advantages. There is no wavelength drift in vacuum application or temperature changes. Also, the online monitoring during the coating process allows more complex coating specifications with a good homogeneity over the chamber. Our chamber has a homogeneity better than 1% of a diameter of 15 inch. This allows a reasonable pricing as a large area can be used and coating on large optics is possible. However, the high dense coating is paid with higher stress on the substrate. This can be compensated if critical for the application, but on a higher effort, therefore the price will increase. Another disadvantage of this technology, especially if compared to IBS, is that there are some restrictions in total layer thickness, and there is not enough coating material available. This will be improved in beginning of 2023, when we are getting the next generation of IAD chamber. Now, IBS or ion beam sputtering could be a good choice in the case of thick layers are needed. This is completely different process. Here we start with a rigid coating material which is sputtered at a high energy ion beam. The coating material is then accelerated with very high energy on the substrates. This is comparable to IAD, and again, one of the advantages and disadvantages at the same time. The high energy allows a high packaging intensity and thus no thermal drift of the coating, but at the same time a high stress on the substrates, which needs to be compensated with extra effort if the flatness is critical for the application. As the material is coming from a rigid blade, there is nearly no limit on coating material, and high reflectivities in very complex coating designs can be done. But the sputtering is a much slower process. If you do the same standard coating with E-beam and IBS, the IBS will take about double as long. But by the way, IAD will be in between IBS and E-beam. Some of the coatings we do for high power laser application takes more than 48 hours. So price is always higher for IBS than for E-beam and ion-assisted deposition. This explains why there is a need of different coating technology. Every technology has its advantages and disadvantages. When doing the coating design, we try to decide which is the best for your application. For example, if you have a rather small beam diameter at your optics, then typically the flatness is not as critical, as the dense coatings typically only influence the sagittal error, and this is not negligible for small beam diameter. However, if you use a mirror or a thin film polarizer under vacuum, IBS or IAD are the choice, and if the reflected beam is used, the bending of the substrate needs to be compensated. This is a well understood process, but it will influence the pricing. We have mentioned LIDT max is best for E-beam. This is valid for standard mirrors and nanosecond pulses. However, we would not recommend E-beam necessarily for a high power CW laser application at 10 kilowatt or more. All this is nothing our customer really must know as we take the decision, but it is helpful for anyone to understand when specifying optics. An overspecification on one parameter might influence you not to get the best result for your application. I could have another talk about trade-off on specifications. If you're interested about this, just let me know. Now you have heard a lot about the coating technologies, and I have mentioned the online measurement before. Let's have a deeper look into this topic now. The first and oldest monitoring dielectric coating is the usage of quartz crystal. The coating material is applied also on this crystal. The frequency of the vibration is changed due to material increase, so the vibration correlates to the layer thickness applied. This is a method which is used since the 60s, but limits the number of layers as the change of the frequency is getting less as more material is on the crystal, and then this is not good enough for high accurate optical coatings. Often coatings are monitored with a monochromator. There, the transmission on a test glass is measured at a single wavelength during the coating. By extrapolation of the coating design, the measurement gives you a good information on the spectral behavior. But this is only accurate enough for designs with lambda/4 stacks, which often is sufficient for standard mirrors and anti-reflective coatings. A rather simple method would be using a timer. But this is only possible for sputtering technologies, as this has a constant sputtering rate. If there is any failure during the coating process, this will not be detected until after the coating is completed at the outgoing spectral measurement on the witness sample. However, this is a good method to be used in the combination with other methods. The trend, however, is now to work with a broadband monitoring system to control the spectral behavior. The broadband monitoring means like the monochromator that the spectral behavior of a test glass is monitoring during the coating process. In this case, the measurement is done over a large wavelength range, for example, over 400 to 900 nanometer. Even if the coating again is not designed in this region of 400 to 900 nanometer, the coating will be extrapolated to the monitoring wavelength range. What is important for all these extrapolations is the index of refraction over the complete wavelength range used. One problem with this measuring technique is still if there is an optics with a high reflectivity or high transmission over the monitoring wavelengths. As in this case, after several layers, there is no significant changes detected on the measuring window. Thus, the accuracy is not good enough any longer. We have two possibilities to overcome this. I want to explain this with one example on how to solve this. We have here the example of a broadband mirror with high reflectivity from 390 to 930 nanometer at normal angle of incidence. To reach the specified reflectivity, a design with more than 100 layers is needed. For the last layers, the change in the transmission is very small and the accuracy would not be good enough to do a good coating, fulfilling all the specifications. One possibility is now to exchange the measuring sample, for example, after half of the layers. The first test sample will see a spectral behavior like the first simulation curve. The second test glass will see the second simulation curve. But this exchange of the measuring sample shall be done during the coating process, so we need some mechanics to replace. This is taking quite some space in the chamber and reduces the capacity of the coating. This is not so critical for small substrates or if only a few parts are needed. What if larger optics or large quantities are needed? Then we have now in our new large IBS chamber the possibility to use two broadband monitoring systems at two wavelength ranges. In our case, 400 to 900 nanometers and additionally 1100 to 2000 nanometer at the same coating run. The 400 to 900 will be used for the first layers till the accuracy is not any longer good enough. Then the second wavelength range will be used for monitoring as there is still enough information available to reach a good spectral result. As I have said before, the index of refraction must be well known. This is a chamber-specific information and something that is verified on a regular basis. This is only one example. Many other designs could be done thanks to those monitoring systems, which were not possible some years ago or only with limitation in the specifications. So what are your future products? Are you looking for some optics that challenges us? Please let us know. You can contact me or my colleague Huyen Wu from our office in the US. Thank you for your attention.